So, good afternoon from me. My name is Yiannis Nikolakopoulos. Do you hear me well? Yeah. I'm the software lead at 0 Point Technologies, and I'm going to talk about some of the efforts we're doing towards a compressed memory tier in the kernel. And this might not sound familiar to some people. So I want to start a little bit before the how. I want to spend some time on the why we're doing this and what's the underlying technology behind it. Because I think some things are different, for example, from contexts like ZSwap that Vitaly brought in, but also some similarities as well. So I'll go very briefly to some fundamental memory problems, which I want to hope that most of us are familiar with. And then I want to talk a bit about CXL and our technology that targets CXL. And finally, how all this gets reflected to the kernel, or how we want them to get reflected to the kernel. So the most fundamental memory problem is that memory is a bottleneck, right? And this goes back to hardware. Like for decades, CPUs were getting faster in a way faster pace than memory was getting faster, right? And this resulted into a huge performance gap. And things are actually getting even worse these days because now memory doesn't scale even on the SRAM level. So with the latest fabrication nodes, you get still double the transistors, but not double the SRAM capacity for the same chip area. So all this makes the memory the big bottleneck. At the same time, you have the energy challenge. This is a funny slide, actually. We've had it in our marketing slides for a couple of years, not a couple, since 2021. And I'm pretty sure now, after the Gen AI, we've jumped this curve way ahead. So I'm very curious, actually, to see the new numbers out of this. So in short, the problem with memory is that right now we cannot feed our cores with enough data, and we cannot feed them fast enough, right? And the limitations here are memory bandwidth limitations. So the memory channels are not fast enough, as the cores need. And pinout limitations are actually thin, right? If you talk with SoC manufacturers or CPU manufacturers, they will tell you they could actually be producing CPUs with hundreds of cores, but they cannot put enough DDR controllers on them so that they get enough memory. At the same time, despite all these challenges, memory cost is still a dominating factor in total cost of ownership. So in the data center world today, memory is 50% of the capital expenses and 20 to 30% of the operational expenses. So memory is not as fast as we want it, not as fast as we want it, and still expensive. So one technology that, to some extent, amongst else, I would say, tries to address some of these problems is CXL. May I ask how many of you have heard of it? OK, that's not too bad. Better than expected, I have to admit. So CXL is a new interconnect, the one interconnect to rule them all. Famous last words, I know. Which basically tries to create a protocol for any CPU to device connection. It builds on the physical layer upon PCI Express 5, and actually with the latest CXL versions, it bumps to Gen 6 and later Gen 7. And the idea is that it maintains memory coherency between the memory space that the CPU sees and the memory spaces of the devices, right? And the vision there is to be able to pull all sorts of devices and memories in a coherent address space that you will be able to to address, whether you are running code on CPU or on the device, or even between shared memory even between hosts. There is a big vision there. So this should allow pooling of resources and to allow higher performance and reduce software stack and reduce complexity. My personal opinion, I'm not so sure about the reduced complexity yet, at least. But overall, they're hoping for a lower overall system cost. And the first real use case that we see in CXL is memory expansion. So imagine that you have a host and that it has a CXL controller that allows you to plug in devices that eventually are expansion cards with memory. And you can even have a switch in between or not. That actually adds some latency. But still, the idea is that this allows you to extend your memory, the capacity of the memory of your host. And this can scale using the switch protocols there. So this gives you more memory per core, more higher bandwidth per core, for this memory, because actually the CXL protocol allows you higher bandwidth, and using interleaving and other techniques, you can achieve higher bandwidth than even native memory, but at a latency cost, which it looks like it will be a manageable cost, at least for a big category of the use cases. Or that's an open question, let's say. So the situation then in memory looks somehow like this, right? The traditional memory pyramid, as we knew it, you have registers and caches on top with very low latency, main memory with 80 to 140 nanoseconds latency, and then CXL memory is the new entry there with roughly double the latency, let's say, or a little bit less than double, ideally. And then we follow on with NVMe, SSDs, and so on. Or even disaggregated memory somewhere there with RDMAs. And on the host side, on the CPU side, what changes is now the CPUs can replace some of the DDR controllers with the CXL PHYs, which are actually smaller in area. And then behind the CXL controller, you can actually have any type of memory that you want. So that it gives an opportunity to have agnostic, like you have a memory interface agnostic to how it is backed up with what kind of technology. It could be DDR4, DDR5, or anything exotic. So how does this look like in the kernel right now? I should say that there is a CXL subsystem in the kernel. There is a lot of work being done there by lots of good folks. And there is a big part of the standard already supported. The majority of 2.0, I would say, and a lot of 3.0 features are there already. But that's the CXL subsystem. Now, how do you use that memory? Actually, allow me to go back. Like, the pyramid here is just latencies, right? It doesn't tell us anything about how the memory is used. So in this talk, I will focus a lot on memory tiering. It's not the only use case of CXL memory. I mean, you can use it as memory business as usual, but still, that's if you can carry the latency cost. In the memory tiering case, what happens is that, so let me actually dig a little bit deeper on how does this memory look like from the kernel's point of view. What happens is the system firmware will identify, I mean, it needs support on the BIOS firmware level. So using the ACPI tables, the system firmware will inform the kernel that, look, you have, for example, node 0 that has your CPUs and memory, node 1 that has another bunch of CPUs and memory, and you actually have an extra node that only has memory. So it's a CPU-less NUMA node. And as part of the ACPI, there are some tables that inform the system with latencies and bandwidth. And there it is reported that actually this tier has even higher latency than the standard memory. And if you have delved into ACPI before, you might know that there are what they are called proximity domains. And in principle, CXL memory usually is its own proximity domain. Then the kernel, by reading these, is actually defining what it calls memory tiers. So in this case, we would have the first tier that has the two standard sockets of your server and the NUMA memory that is there. And then the second tier that has only the CXL memory. The idea is that the pages are placed on the different tiers based on either mem policy, but I'm not going to dig too much into this, or hotness. So in principle, the reclaim path, as it is right now, when the kernel is under memory pressure, will identify the latest parts of your LRU or MGLRU, whatever you have configured. And the cold pages, in principle, instead of getting to, before they go to swap, they will first go to the remote CXL memory. So this is now up, this is mainline. There are some easy ways to configure it. I actually have a nice blog post if you want to play with it, even in QEMU. And there has been quite some research about the memory tiering systems. I have two important papers here. So one was by Meta, where they basically showed how they identify which pages are hot and which pages are cold using a technique with minor page faults. And then based on this identification, they migrate the cold pages to the remote tier. And in fact, a big part of this paper is now part of the mainline kernel. It's what we have as the migration logic there. At the same time, Google presented another idea, actually extending some of the work they had done, I think, for NVMe storage and for the 3D cross-point memory, actually, where they use another mechanism to identify cold pages, but still using the kernel migration mechanism to move them. So there is a lot of effort being put there. And of course, after these, there is tons of research papers, both from academia and industry collaborations, looking into different corners and how you can optimize this better. But what's interesting to keep in mind is that while we have the pyramid with the latency, that's not the only part that this pyramid shows. There is a cost involved there. And we usually, every layer of this pyramid, we go from the more expensive to the less expensive. And this is not what's happening at the CXL memory, or not what has been happening so far. And this is one of the reasons that this has not been adapted that much. Because why would you pay the latency cost if this is still as expensive as before, right? So the cost needs to follow the trend. And there is a very nice webinar, actually, by Google and Meta, which I reference here, and I'll outline the main points. But in fact, this is building up on several of these memory tiering research papers that we have seen before, and even existing experience on ZRAM and ZSwap deployments, right? So basically what they know, the hyperscalers, is that half of their memory, like this expensive memory that you have on the data center, half of it has not been used in the past minute, right? 50% of your memory is basically cold. And we do know that in practice, all these cold data have good compressibility. And both from research, but also that's why there are so many ZRAM and ZSwap deployments on the data center world. And this cold data, when you need to access them, usually requires roughly 1% of the system memory bandwidth. So you don't even need high performance for accessing the cold data. So if you put all of this together, it looks like a compressed memory tier makes economic sense. Because if the 2-to-1 compression ratio is realistic on the majority of general purpose workloads, that means you can actually halve the media cost for the CXL memory, in principle. And that's why, like 1.5 years ago, Google and Meta published an OCP in the Open Compute Project, a specification for CXL memory expanders, and there they defined the requirement for compression. So to tie all this story together. Now, on our end, as 0 Point, we have been working on technology of for hardware accelerated compression for the last 8 years. And we now have an IP that targets the CXL market. And I'm not going to go too much into the details or the technical specs. I'll give you a very high-level view, and then what's interesting from the kernel's point of view is the interface and how does this IP behaves. So our DenseMem IP is a solution for CXL devices. You would typically see it on a CXL device, and as memory transactions go through the CXL controller down to DRAM, they are intercepted by our OEP, compressed in line or decompressed in line. And then we also take care of the memory management on the device side, and they are compacted and stored on the device. So the value proposition here is reduce TCO of the data center by 15%. And we actually provide multiple compression algorithms on this IP. So both proprietary and open source, like LZ4. Of course, not the hardware implementation, like open data, open standard algorithms. And please interrupt me with any questions. Should have said that from the beginning. So how does a tiering memory, how does this look like from the host point of view? So this is a conventional tiered memory, right? You have on the left side tier 1 with a directly attached memory on the host, and the CXL controller with a tier 2, the CXL memory. And typically when a page would be migrated, would go through the CXL controller, there is this concept of host physical address space, which is what in the kernel we call physical address, most of the times at least, which goes through the CXL controller, then the controller translates it to the device physical address space, and that goes and sits somewhere on the device. So this is the baseline. Now what happens when DenseMem is there is that, let's say there is a third tier now that we manage with our DenseMem IP. And what we do is that we actually lie about the capacity. So if, for example, this is 1 terabyte, we're going to say, OK, this is actually 2 terabyte. We oversubscribe the address space. And then how does this work in practice? When data goes through, our IP intercepts it, compresses it, and compacts it. And that's how we save space. By compressing, compacting, and remapping the addresses, we expand the memory capacity. Yep.
What happens when you make a malicious workload that doesn't compress?
That's the main question. Yeah, I'll get to that. So for this reason, the host doesn't know the real capacity of the device. So we need somehow to report the capacity back to the host. And to let the host react upon changes of this capacity. So there is an API. I didn't go into the details of the CXL spec, but In principle, all these memory transactions are, in the CXL, they are called .mem. They are typical memory transactions that the CPU sees, right? They just go through the CXL controller. But then there are, of course, since this builds upon PCIe, there is the .io protocol of the CXL, so you get a control plane on the PCIe configuration bars, in principle. So there we have configuration knobs about, okay, how much do we want to oversubscribe the memory? Like how big is your backing media and how big you want to oversubscribe. And then through this .io path, we provide telemetry that reports back the actual remaining capacity. So this is the sideband so that the host can see how much memory do I actually have. At the same time, there is a mechanism where the host can configure 4 watermarks, like high, medium, low, critically low. And as the capacity crosses, the remaining capacity crosses these watermarks, it will actually raise an MSIX interrupt to the host. And then we expect the host to do something there, right? At the same time, we might be doing stuff on our end, on the device side, to help and mitigate the situation, like additional back pressure on the right bandwidth, or change the configuration of the compression algorithm and other things, or defragmentation, for example. And finally, there is an additional command for freeing capacity, which is basically like a trim command, since I know there are a lot of people from storage space. So the host software is expected to utilize this interface in order to lower the write utilization as we run out of capacity, right? And going back to your question, once these malicious workloads comes, which it doesn't need to be like, I would say adversarial, right? I mean, it might be that somebody is writing high entropy data and it kills your compression, right? So then you would slowly start getting these interrupts, and you should probably, depending on where you have this hooked, you should stop writing data, basically, or start reclaiming data. So last year, I presented this API in LSFMM, in the memory management track. And because I wanted to get some first feedback on how we could support this upstream. And of course, people were fairly skeptical about this. One common point was, you're adding latency overheads on something that is already expensive. And I understand that because there is a big part of the community that sees CXL as fairly high latency memory, and they don't like it. And I can understand that. So they are wondering, okay, how much worse are you making things now with compression? So the number if this is of interest, I can show it in the end. We actually have data sets from our technology. I think we have a very good answer to that. And depending on the access pattern, actually the latency can be completely hidden. And just to give you an idea, the overhead we're talking about with our proprietary algorithm sits on the ballpark of 80 cycles to decompress the critical line of a block. So it's actually not that bad. No, that's an understatement. It's actually very good. Now, the second problem is corner cases of the capacity back pressure, which is, again, your question, Andreas. So the consensus from that session is that if we try to utilize this in the kernel, it should be something that looks like Z-swap, swims like Z-swap, and squawks like Z-swap, right? In the sense that they want it to be able, it should be somehow self-contained so that you can reject writing data onto it. And for example, in ZSwap, you can do this, right? If ZSwap runs out of memory, it can always reject a store operation. And then the kernel will follow another path, like it will skip the cache and will go actually to disk. And the other part is that, yeah, because they are afraid actually in these cases of the adversarial workloads that you don't want the kernel to be forced to more memory pressure than what it already had. So there is a tricky situation there. But on the other hand, the main difference from something like ZSwap, and that's our requirement at least, and not only our, but also our customers' requirement, is that this, whatever way we integrate this, it still needs to keep the pages mapped, right? Because when pages reach ZSwap, they are unmapped, and if you need to read them, you need to page fault again. I mean, the whole idea of the CXL memory as a remote memory tier is that, yes, I'm going to demote my cold pages there, but the occasional read I have, I can still serve it on a cache line level, right? And on our end, we have the compression technology to do that extremely fast, even if we need to decompress that cache line. So we shouldn't be, we shouldn't incur a page fault overhead here. So it cannot really be on the swap path. And since then, of course, there is some time has passed, but we depending on the priorities, we had to work on some other stuff. So now we have done some first prototyping, and I'm fairly open. This is really work in progress, and I would categorize it on the pre-RFC state. But I think it's interesting to see a little bit the idea here. So the assumption is that the compressed tier is the lowest tier, right? There is nothing else below. And that's easy to fix with how you declare the device over the ACPI tables, right? Because what I didn't say before is that this whole memory tiering is actually arbitrarily long. Nobody forces you to have just 2 tiers. It could be 3 or 4 or whatever. And what we looked into is how to intercept the folio demotion path. Now, let me recall what I said before is that, in principle, how the demotion path works now is that on the reclamation path, if you, which is actually all sorts of reclaim paths go through this shrink folio list function, which tries to gets a list of folios and tries to reduce them. And before actually triggering the swap path, it will call this demote folio list. And we'll try to demote to a lower tier. So inside this demote folio list, what happens is that it finds the next demotion node. So depending on the hierarchy you have of different nodes, you will get the next one. And that's why I'm saying now I'm assuming that the node with the compressed memory is the last one on this. So that if it cannot demote there, then it will go to swap, which is business as usual. And there it calls the migration functions passing an allocator function, which is called alloc migrate folio. So in principle, what happens there is this MTC structure, which is basically the node information from the NUMA topology. And so that should have identified the compressed node in principle. And it will try to allocate memory from the, so what migrate pages will do is it will try to allocate memory from that target node. Again, this is kernel code, lots of sub cases there. It will check first if it's a huge TLB page or whatever else. But still, the idea is the same. And this alloc folio function, alloc migrate folio, is passed around actually in all the subsequent calls in there. And that's what sounds like a nice place to reject if you are running out of memory. Because it is an allocator function. So this is where we believe we could actually check, okay, am I running on a compressed node? Like, is my target a compressed node? Yes. Does it actually have remaining capacity? Because yeah, there is what the allocator says, but then I can check the hardware to see, okay, do I still have remaining capacity? And then if I have, sure, go ahead. If I don't, we can actually fail there gracefully with any no mem. And then the kernel will do whatever it has to do, that is, go to the swap path. So with some first tests, this actually seems to work reasonably well. But again, this is a dirty prototype, and what's difficult here is to cut through all the abstraction layers that are hidden. So that I haven't solved yet. So let's see, though, some of the not so early problems here. One of the fundamental complexities here is that CXL memories, like even if it does something fancy like compression, transparent compression like we do, it's still a memory interface. So the device side doesn't know if the memory is used or not, right? It only sees memory transaction. It doesn't see anything else. So how much memory the device has used because of how much we have compressed and compacted the data can actually be completely different from how much memory the kernel has allocated. And to make it more clear, imagine, so I allocate a bunch of memory. I write my entire device. Then my workload finishes. Memory gets called, gets freed. But the device doesn't know that this memory is actually freed. And then when you try to rewrite to that memory because a new workload starts, the remaining capacity actually doesn't make sense on its own. So you need to compare both what the remaining capacity says and what your allocator stats say to get a ground truth, which again makes the code and the logic fairly ugly there. But one way to tackle that would be to add hooks to the free commands of the core kernel allocators. But I'm very afraid on what people will say if I'll try to do that. Because that not only helps with understanding the remaining capacity, but there we could actually use, for example, our trim command and make actually the freeing even more efficient there. Then I mainly talked about the core idea is to plug in this telemetry, basically, of the remaining capacity. But I didn't talk about the MSIX interrupts. So what happens when they are triggered? I mean, can we utilize them? Should we utilize them in the kernel? And the rough idea I have here is that we could actually use them to trigger the reclaim path asynchronously so that you can actually swap out memory from the compressed tier, at least on the low or critically low cases. I mean, the rest could be just information to the kernel. Now, the other part that is still getting complicated is that tiering, which is what I have focused on here, is not the only way you touch memory, right? For example, there are mem policies. So you can, if the entire system is under memory pressure, yes, maybe your tiering path will reject writes to this remote memory. But actually, if there is nothing on your first memory tier, if there is no memory left, it will still try to allocate memory from the remote device. So do we put more checks there on the core kernel allocator? That's another problem. Or do we use it just by, for example, a good first start would be to use it with policies that disallow remote allocations completely, so that you only tiering touches that node, basically. And the final part is that all these requires information from different layers of abstraction. So it's going to be a little bit of a pain to figure out what's the right abstraction layer, or if we need to create something new, or how to propagate the information around. Yeah, so to conclude, what I would like you to remember from this talk is that, yeah, CXL memories in general are trying to tackle some of the fundamental memory bottlenecks. There is a clear need for a compressed memory tier. And yes, I talked a lot about CXL, but this is nothing new really, right? We have been using a compressed memory tier in the form of ZRAM and ZSwap for a while now, right? This is just a faster one because it's implemented in hardware, basically. The compression technology is here, and I'll shamelessly plug and say we are proud to have some of the best technology in this field. And the challenge is to find the right abstraction for bringing this compressed tier into existence, while trying to avoid or minimize at least the impact on the core memory management code. So thank you very much.
So do we have any questions? Oh.
Okay, so I have a few, but I will try to be fast. First of all, one small comment about your research of free path. I believe you know that free must be atomic, right? So you cannot do much there.
Yeah.
Yeah. So then the second is to continue during this, the presentation was question about the malicious or whatever compressed data, let's say. You also mentioned that you ask hardware to check how much memory is available, but you don't know how much, how big ratio of compression ratio will be. So it means that you ask for memory, let's say, it will say on hardware you have like 100 megabytes, right? And then if you put 100 megabytes of data which already compressed, it's different of 100 megabytes with which data is, can be compressed, right? So at the end, it might be some piece of storage which will be left unused. How much, how big is that? Have you checked?
So if I understand the question, you're saying, given that the remaining capacity is actual free bytes, and when you put data, they get compressed, that you won't utilize the whole thing, right?
Right.
Yeah.
Utilization, yeah.
And that's why this is a continuous loop here, right? So the idea is that the host, like on a location, knows the entire address space, and like if we don't expose any of this sideband, we just try to allocate and write, okay? So the answer is, yeah, if, for example, it's 100 megabyte left, and I write 100 megabyte, but they actually occupy 50 megabyte, then I'm gonna see still 50 megabyte left, right? So I'm not gonna force anybody, I'm not gonna stop the next 100 to go there. So that's why we wanna have this loop like frequently checked in that sense.
Okay, then quick question about, you mentioned at ACPI. Does it apply for ARM platforms as well?
Yeah, I don't see any reason not to.
So I mean, basically, the ACPI tables that here you mentioned it, they are generic, right? So it doesn't matter what CPU or architecture.
No, it's okay.
Okay.
Yeah, it's part of the CXL spec to produce some CDAT tables, which then the firmware will produce the appropriate ACPI tables from them. So this is standard CXL.
Okay, and last question about hardware. Can CXL memory be located on Thunderbolt device? Because
Honestly,
Thunderbolt could provide PCIe
Yeah.
over Thunderbolt.
I have to admit I'm not aware. Given that it's PCIe, probably. I honestly don't know. I don't want to give an answer.
Yeah, and the last quick question, is it hot pluggable or not? Because of Thunderbolt question.
I'll need to think about that.
Hi, I was wondering about, I saw an interesting video about CXL, and they were basically using a PCIe card that they stuck in a PCIe slot. Basically the way it was explained was that it was a sort of interim, in case you need to upgrade in the middle of an upgrade cycle, instead of buying an entirely new hardware, you could just increase your RAM. But I was also wondering, regarding the increased latency, do you have to account, like when you have cache, for example, you want to be very specific about what you put in the cache. Do you have a similar way of differentiating what data is more important that you then put on the actual RAM versus the one you put on the CXL RAM?
Yeah, the kernel basically is already doing it with this this hotness path. I mean, honestly, the most fundamental way that you can do it is the existing LRU of the kernel, right? The least recently used pages. I mean, that still gives you an idea on how frequently a page has been used. So typically, you would demote the coldest parts of this page. Yes. There are more and more sophisticated mechanisms about this, but there is already something working to give you an answer there.
I'm sorry to interrupt. Yeah. You will have to continue on the walk home.
Thank you.
To the burger place.
Yeah,
thank you very much.